Cool. So let's get started with the session. So today we are gonna study about segment trees, and I'll be discussing it in a manner so that even if you have not studied about trees in general, even then you'll be able to understand that. But I believe that without before even starting with a particular topic, we should at least know that why we are studying it, right? So for that reason, the first thing we are going to talk about is that why. So why do we even want segment trees? Don't we have simpler data structures that can do the stuff we want to do with segment trees and stuff like that, right? So the very first question is why do we want to study it? Now let me say that I give you an array, right? Array of elements, and I ask you that okay, so there are some elements in it like 1, 2, 4, 3, 5, anything like that, and then I ask you to give me the sum of elements from 0 to 3 maybe, right? So this is 1, this is 2, this is 3, this is 4. So you'll say that okay, it's easily doable in order of n. So you'll give me this sum. You'll start a pointer from here. You'll calculate the sum as 1 plus 2 is 3 plus 4 is 7 plus 3 is 10. You'll say that okay, so the sum is 10. So I said, okay, good enough. But let me say now I give you q queries, or I'll give you n queries in total. So now you'll say that for every query, I'll be doing this operation. So the order of overall complexity would be order of n square. Or if the number of queries is q, so the complexity would become order of nq, right? Now I'll ask you to decrease it further. So you'll say fine enough. So I can actually create a presum matrix from this. Now, what is a presum matrix? Presum matrix just contains the sum. So the array we were having was 1, 3. Okay, 1, 2, 4, 3, 5, right? 1, 2, 4, 3, 5. So when I'll create the presum matrix, so it would be 1. 1 plus 2 is 3. 3 plus 4 is 7. 7 plus 3 is 10. 10 plus 5 is 15, right? So you will say that, okay, I've created this matrix. So I'll ask you, give me the sum from 0 to 3. So you'll say this is the 0, 1, 2, 3 index. So you'll say that the sum is 10. I'll ask you, give me the sum from maybe like 1 to 3. So you'll say that sum is 10 minus whatsoever is before 1, right? So what the value at 3 minus the value that is before 1. So that's 1, right? So you'll say, okay, 10 minus 1 is equal to 9. So this is an easy way of doing it. So you'll say I can do it in order of 1, right? You just have to access the elements. So for building, you need order of n time. For accessing, you need order of 1 time, right? So that's cool enough. So your overall complexity becomes order of n plus q. That's pretty good. But now I ask you that, okay, what I want you to do is that, so one of the queries is that I want to get the sum of some range. So I want to get the sum from the range L to R, but there's a different kind of a query. So I'll ask you to update one of the elements that is at location, at any location L, let's say, right? Its value should be updated to maybe something like V, right? This is one kind of operation. So now what would happen is that since this was the array that was 1, 2, 4, 3, 5, right? Now I ask you that update the element at index 2 as 100. So now you'll update it as 100. But now if you want to process the queries again, so you have to build your presum matrix again, right? So you'll have to build it again, or you'll have to start building it from the point where you have already updated it. So from log up to so on, you have to update it. So because of this operation itself, it's gonna take you order of n complexity in this building operation. So the complexity again becomes order of n square. Now this becomes a problem because we don't want our complexity to be order of n square. We want better than that. So what can we do? So over here we get a concept that is called segment trees. So a segment trees allows me to get the sum. Like sum is just an example. You can perform a lot of other things as well, like getting the maximum element in a range or a minimum element in a range. So basically range operations, range find, I'll say. So finding the sum or maximum or minimum or XOR, anything like that, right? So you can find in a range in order of log n time, and you can also update a single point. So you cannot update a range over here. There are variations where you can update the range. That is known as lazy segment tree. That is not the point of discussion for today. So today we'll be just discussing about the point update. So what do I mean by point update? I'll simply say that, okay, update the value at location to the new value we knew. I can't ask you to update the value from location L to R or in the range L to R to some new value. This is not a valid operation that I can do. I hope that makes sense. Right. So point updates and range find are the two things we can do using segment trees. and both of them can be done in order of log n operation, right? Order of log n complexity. So if you have q operations, the overall time complexity becomes order of q log n, which is something we wanted, right? Because earlier than that we were having a time complexity of order of nq. No matter what we use, if we are using a pre-sum matrix or whatever sort of a data structure we were using, we were getting this particular complexity. Now order of nq actually has a greater time complexity than order of q log n, and hence this satisfies our criteria or what we wanted to achieve. Up till this point, does anyone have a doubt? Okay, cool enough. Let's move ahead. Guys, if anyone has a doubt at any point in time, please let me know, right? So that clears the first point, that why we need a segment tree. Now what is a segment tree? Now this is a classical example of a segment tree. Now what is this? So this actually is a sum segment tree, right? Wherein you have elements from 0 to 7, or it's an array of 8 elements, and the elements in the array are 2, 6, 4, -3, 5, -1, 6, 10, right? Now how would you perform, or how would you get the sum when I ask you, right? So let's say I ask you to get me the sum of all the elements, right? So you'll go over here, you'll directly fetch that the overall sum is 29. I ask you to get me the sum from the for the elements in the range 0 to 3, right? Or from the index 0 to the index 3. So you'll say that okay, this is this is of the range 0 to 7, right? This particular node denotes whatever elements are there in the range 0 to 7. So you'll say that okay, so the middle point over here becomes 7 divided by 2. That is equal to 3.5, but integer division gives us 3. So that means the elements from 0 to 3 would be available at the left hand side, and the elements that are greater in the range greater than 3 or from range 4 to 7 would be available at the right hand side. Don't worry, I'll dry run it and then it would become more clear, but just giving you a perspective, right? So you'll go over here, you'll say that okay, what this particular node signifies, or what this particular node contains. So this particular node would contain elements from 0 to 3. You'll say that that's exactly what I want, so I can return 9. Now what if, now let's change it a bit. Now I want you to calculate the elements in the range 0 to 2. So you'll perform the same operation. You'll go over here, you'll check that okay, like 3 is the mid, so I need 0 to 2 elements, or the elements in the range 0 to 2. So it would be available to my to my left. I'll go to my left, I'll reach over here, I'll ask okay, what all elements do you contain? It will say 0 to 3. Then I'll ask him that can you like, you already contain 0 to 3, what's your mid? So I'll say okay, my mid is 2. Then I'll ask him that okay, so your mid is not 2 but 1. Yeah, so 3 divided by 2 is 1.5. The floor operation gives us 1, or the integer division gives us 1. So I know that okay, the elements from 0 to 1 are available in my left children, and the elements from 2 to 3 would be available in my right children. So I'll say okay, get me the firstly the elements from 0 to 1. So it will get me 8, right? Now I'll go over here, I'll ask that okay, you have how many elements do you have? It will say that I have elements 2 and 3, right? Or the elements at index 2 and 3, but I only require 2. So I'll ask him that okay, give me the element at index 2. It will get me this particular element, that is 4. So it will return me a 4, it will return me a 8, whose sum is gonna be 12, right? So that's what we are gonna get. Let me use my iPad maybe, so I can explain this particular scenario in a bit detail. Let me just draw it a bit. Give me a second. 29, then we have a 9, then we have a 8, then we have a 1, then we have a 2, then we have a 6. Okay, 4 and a -3. Then we have a 20, 4, 16, and some values which I don't care about. Okay, so let's move over here. So this is the segment tree I was having. Now over here, one thing to note is that the array elements, or the array elements were these actually, right? These ones. So every time in a segment tree, the array elements or the actual elements would be represented by the leaves itself. The internal nodes always represent some range. So for example, this was the element at index 0. Let me mark the index with some other colors. So maybe green. Yeah. This was the element at index 0. This was at 1. This was at 2. This was at 3. At 4, at 5, at 6, and at 7, right? So these were 8 elements in total, right? So this was the element at index 0. This actually represents the element from index 0 to 1. Now since this is a sum segment tree as I told you, so this contains the sum of these two elements, that is 0 and 1. Right? So the sum is contained over here. What's the sum of 2 and 6? The sum is 8. Now what about these two nodes? These are the leaf nodes. It contains the elements at index 2. This contains the element at index 3. The parent node would contain the element at index 2 and 3, right? So its sum is 4 minus 3. This is minus 3, right? 4 minus 3 is 1. So 1 would be contained over here. Let's try to go up a bit now. Now what about this node? Okay, yeah. Now what about this particular node right over here? So this would contain the range of its children. So its children is having a range 0, 1, right? And this is having a range 2, 3. You combine them up, you get a range from 0 to 3, right? So this particular element contains the range 0 to 3. Now what's the sum? The sum would be 8 plus 1, that would be 9, right? And similarly the same thing would happen over here. Now explaining the same thing would be trivial and a waste of time, so I won't be doing that. But I hope you get the drill that how a segment tree is actually constructed, right? Now how do we construct it in a code is also simple and it's pretty intuitive. I'll be explaining that in a while. But the entire motive over here was to explain you how it actually looks like and how it actually works. Now over here we had a perfect or a complete tree because we were having eight nodes, and 8 is actually a power of 2, right? So power 2 to power 3 is actually 8. It's possible that let's say you have 3 nodes in total. Now 3 is not a power of 2, so what would happen is that this node would actually represent 0 to 3. That would be the total, right? Now you will say what is the mid? So the mid is 1. So 0 to 1 would be represented by this. 2 comma 2 is represented by this. What do we mean by 2 comma 2? So 2 comma 2 is a single element, right? So this would represent the node itself. So it would represent the array at index 2, or the element at the index 2 of the array, right? And this represents the range 0 to 1. So this can be broken down further, right? So this would be element at 0, 0. This would be element at 1, 1. So this also is a segment tree. So a segment tree is basically a binary tree wherein each node contains the sum or some of the operations. When I say it could be either sum, right? Or it could be some other operation. It could be a maximum or a minimum, right? It contains these kind of things for its children nodes. And that's all what a segment tree is, right? Now one thing we already discussed is that how to get the sum out of it, right? If you want to discuss it further, I can give you a simple example. So let's say you wanted, okay, so this was 0 to 7, right? I want you to get the sum from 0 to 4 maybe. Cool. How would you get that? Let me erase the extra stuff. Okay, fine. Okay, I erased 9 also. I'll repopulate that. This is 9. Cool. So I want you to get me the sum of 0 to 4. How would you get it? So you'll say, okay, what's the mid? It will say the mid is 7 minus 0 divided by 2. That is actually 3, right? So you'll say, okay, so 0 and 3 would be present on your left, and that means 4 to 7 would be present on your right. You'll say, yeah, right. So you'll say that, okay, I need from your children that is present to your right or to your left, which has the elements from 0 to 3, get me the entire range, because 0 to 3 is itself a part of the range 0 to 4, right? So you'll say, okay, get me the entire range from this. He'll get you the entire range. That would be 9. Then you will come over here to your children that actually contains 4 to 7. You'll say that get me only 4. Cool. So it will go over here. He'll say that, okay, get me 4. So he'll say that, okay, I am actually containing 4 to 7, and my mid is 7. Okay, so the mid over here would actually be 7 minus 4 divided by 2, and you will add 4 on top of it, right? Okay, so the value basically how do you calculate the mid is low plus high minus low by 2, or you can simply say high plus low by 2, right? So if your high is 7 and low is 4, so it becomes 7 plus 4 by 2, that is 11 by 2. You round it down, so it becomes a 5, right? So you will say that, okay, so from 4 to 5 elements would be present in this node, and from 6 to 7 elements are present in this node. Then you'll say, okay, if 6 to 7 are not required because I am having a smaller element, so I only require elements that are in that particular range. So ask your left child that is containing 4 to 5 to get me the value of 0, 4, right? Okay, so with that the thing becomes easy. Your child node would get you the value of element at index 4. That would be some value. Let's call it maybe 6, right? Let's call it any value. So it gets you that value, and then you throw the value back. I know it became a bit messy while explaining it, but that's how computer science is. When you are trying to dry run the code, it tends to become messy, but you have to understand how the things work. So I hope this explanation was clear. Right now, we have not discussed how to update a element, and how to how does it actually work in the code. But I wanted to know that up till this point, is everything clear? Okay, guys, if anyone has a doubt in between, you can just interrupt me and ask your doubt right away. Cool. Okay. So with this,
I
yeah,
just want to ask, like, how will we make it in code, and what will be the time complexity for it?
yeah, sure. So we are gonna discuss that. So I'll be discussing the code with you, but firstly, I wanted to make you understand that how it actually works, right? After that, I'll be discussing the code itself. Cool.
Yes.
Okay. So now comes the point that how would we update it? So let me use the same example. Right. Let me just clear it a bit. Okay. This is cleared. This is cleared. This is cleared. Anyway, I'll just use the left part of the tree. So that should be enough for me. Cool enough. Rishikesh, can you like mute your mic, please? Ganesh, you have a doubt? Okay, cool. Okay, so over here, let's say that I ask you to update the value at index 3, right? So I'll ask you that update the value at index 2 maybe. So update the value at index 2 200, right? Now you don't even know what the value is, but I simply ask you to update the value 200, and you're gonna do that. So what you'll do, you'll come over here at the first node, you'll say that okay, what's the mid? So my mid is 3. The value I want to update is 2. So that should be present to my left, right? So I'll go to my left. Then I'll say that okay, what's your mid now? So you'll say that okay, I represent the values from 0 to 3. My mid is actually 1. So that means that the left tree contains the value 0 1, and the right tree contains the values 2 3. I'll say cool. So I'll have to go to the right tree because 2 is present in 2 3 itself, right? Then I'll go over here. Then I'll ask that okay, what do you contain? He'll say I'll contain 2 3. My mid is 2 plus 3 by 2. That is 2 itself. So the left part contains 2 2. The right part contains 3 3. I'll say okay, I wanted to update 2 2, so I'll update that. So I'll come over here. I'll update it as 100, right? Now as soon as I do that in a recursive call, I'll be going back, right? So as soon as I'll go back to the parent node, I'll say I was updated. So I'll now my parent would say that okay, I also need to update my values. So for a parent, updating the value is actually pretty easy. What it can do is that it can ask both its children that what's your values. So over here now the value I'm having is 100. Over here the value I'm having is 3. So the value becomes 97, right? Then I'll go above. Now to the parents, I also say that okay, I was updated. So for this parent also needs to update its value. It will ask me the value, what's your value and what's your value. So it will ask the values from the left tree. This is this one, and the right tree. The right tree would report the value as 97. The left tree would report the value as 8. It will add both the values since it's a sum segment tree. So the value it will now get is 105, right? Now it will go up. It will say that okay, I was updated. So he is again gonna ask me, yeah, any doubts? Okay. So he's again gonna ask me that okay, you are updated, what's your new value? He'll say that okay, 105 is the value I got, and it's gonna ask this node that what's the value you got. So he'll say that okay, I have the value 20. So he'll again update its values to be 105 plus 20. That's gonna be 125. That's it. So that's how updates work. So updates are actually pretty easy. So is that clear, guys? Is that clear?
Yes, yes.
Okay, cool enough. Now, someone asked me that how do we build the binary tree, the segment tree, right? And what's the complexity? So for building, you need order of n space and order of n space complexity and order of n time complexity. Although in case of segment trees, there's a constant factor. So let's say you have n array input, right? So for that, you need 4 into n nodes. Now, why is that? I can give you a proof. Actually, it's less than 4, but we approximate it to 4. Now, let's say this kind of a tree you are having, right? So this was a typical binary tree or a perfect binary tree. So for 4 nodes, you required 7 nodes in total, right? For 4 nodes, you required 7 nodes. Right? Now, how is that? So basically, 2 to power 2 is 4. So in the previous node to it, you would have required two nodes. In the previous node to it, you would have required one node itself, right? So basically, you divide it by two. So you required four nodes at the leaves. Then you divide by two. You get you say that okay, I required two nodes before that, and then I required one node before that. So 4 plus 2 plus 1 is 7. But now it's not always the case that the tree would be complete. It could be the case that your tree only has three nodes, right? So in case of three nodes, the tree structure, as I already told you, would be something like this, right? Okay, yeah, like this. So in case of three nodes, the tree actually had 1, 2, 3, 4, 5 nodes. So for three, it had actually 5 nodes. Now we don't want to always compute that what are the exact number of nodes. So we approximate it, and 4 to power sorry 4 into n is actually upper limit. Now since it's a constant factor, it's not that big of a deal, and we can always incorporate it, right? So we use 4 into n as the number of nodes in the tree. Now the other question is, how do we represent this tree? Now it's easier for me to say that okay, this is a node and this is a node, these are all connected, these are child and parents, but how do we represent it? Now let's say I randomly name them as 1, 2, 3, 4, 5, 6, 7, right? It's not random, but yeah, level wise I'm naming them 8, 9, 10, 11. Now what you'll notice is that for every parent, its child have values 2 into the value of parent. This is always the left child, and the right child is 2 into p plus 1. This is the right child. For example, for node 4, right, the left child has a value 8, that is 4 into 2. The right child has a value 9, that is 4 into 2 plus 1. For node 2, it has left child equal to 4, that is 2 into 2. The right child has the value 2 into 2 plus 1. And in an array, let's say this is the array we are having. So let's ignore the zeroth element. Let's start from the first element. So I can call this the parent, right? This is the parent, not cool. So then the element at the second location would become the left child of p naught, right? The element at the third location will become the right child of p naught. Now what about this? Now this is actually the element 4, so this is basically the left child of this element, right? Now what about 5? This is basically the right child of this element. Now 6 would be the left child of this element. 7 would be the left child of this element. I hope you are able to understand that we can easily represent it in an array as well, right?
Yes.
That solves your doubt.
Yes.
Okay, cool. So now if I try to explain the recursion behind it, then it might take some more time. It's easier, I'll say, to understand the no, okay, give me a second. It's easier to understand the code itself. The code is pretty easy to understand. I actually have it written in segment tree snip. Okay, so this is the segment tree. Let me just populate it so that it doesn't show errors. Okay, give me a second. Segment tree snap. Okay, see, this is the segment tree. So I have a boilerplate code for myself. Now the reason of declaring a class and all is it's just easier to understand what the code is actually doing, and it's like less likely to get errors when you are actually coding. Okay, so let's understand what the code does. So firstly, I'll ask it to build the tree. So for building the tree, okay, let me just give you an example, or maybe we can construct a tree itself, and then we can get started with it. Or okay, let's just do it that way. So let me construct a tree. Okay, we'll just get the inputs from the user. That way it would be actually great, right? C in n, and then I'll construct a vector. Now let's say the vector size is given over here. Then I can ask him to construct a segment tree for me, whose name is st, whose value is n, or whose size is n, and the array we are going to pass is v. Okay, I hope that is fine. Yeah, well, that works. So now the array would be constructed, right? Now I want to get the sum. Get st dot get sum in the range from 0 to maybe 4 or 3, right? Let's see how this works, and if this works, or are there any issues with this. Okay, so we'll create a sample test case, one test case in total. The elements having 5 nodes. The nodes are 1, 2, 3, 4, 5. It is as simple as it can get. Let's test it. Okay, we got a big error. Now why is that the case? Okay, we got it. Okay, got it. Actually, there's this boilerplate code should have been placed below it. Okay, let me try again. Okay, So we get a value 0. Now why is that the case? The value is actually wrong. Let me see it. Okay. We populated the array over here. We said them that okay, I need you to build me a tree, and I gave it the values. Okay, we didn't take the vector itself. Okay, let me see. Okay, so now we are getting a value 10, right? Now is that the correct input? So 0, 1, 2, 3, right? So 4 plus 3 is 7, 7 plus 2 is 9, 9 plus 1 is 10. Now let's try it again. Let's say this. Okay. So 1 to like elements from 1 to 3, it's 2 plus 3 plus 4. So 2 plus 3 plus 4 is actually yeah, 5 plus 4 is 9. Let's try to update some values. So st.update. So I want to update the element at index maybe 2. I want to set its value as 100. I can do that. Then I'll again try to print the answer. Let's try it. Okay, so I get a value 106. Now why is that the case? So this is the element. Yeah. Someone has a doubt? Bro, you can actually text over here. Okay, nice. Anyway, if there's no doubt, I'll move further. So what it did was that it updated the element at index 2. That was already 3, so it updated it. It made it as 100. So now the elements are 1, 2, 100, 4 and 5, right? Now I ask him to get me the sum of elements from index 1 to 3. So it returned 2 plus 100 plus 4, that is 106. So have we validated that the segment trace is working fine? Someone's mic is on. Can you please mute it? There's a echo actually. Oh, I'm gonna yeah. Cool. Okay, so the segment tree is working fine. Now let's understand how it works, right? Don't worry, I'll give you the exact template, right? So that the benefit of having this template is that let's say in a contest, you know that okay, segment tree is going to be required, but you don't understand the functionality of a segment tree completely, right? So you can still use it. So the functions are already pre-written, so you can actually utilize it directly. So let me try the segment tree now, or let me try, make you understand what it does. So this is the constructor, right? I pass the size of the tree and the vector itself, right, to this constructor. Now it says that okay, n is equal to sd. That's basic stuff. Now that then it tries to initialize the tree vector. Now tree vector is the vector which actually represents the tree, or where I told you that the nodes can actually represent parents and child. The first node can represent the root, then second would represent its left side and so on. And I also told you that we take its size to be 4 into size, right? So the size is defined, size is 4 into size over here, and all the elements are initially initialized to 0. Then I start building my tree. Now when I'm building my tree, so the build trace function is over here. So to this I pass the vector that needs to be populated, comma, the indices, that is 0 and n minus 1. Now why 0 and n minus 1? So 0 is the leftmost limit of the array, and n minus 1 is the rightmost limit of the array. That's simple. Also over here, I have actually initialized v. So what's v? V is actually the node. The node is v, right? So we'll always start at the node 1 or at the root node. Then I'll say that if TL is greater than TR. Now what is TL? If the left limit is greater than the right limit, so we are trying to access something negative, right? Or something that doesn't even exist. So in that case, I'll return if my TL is equal to TR, right? What does that mean? So that means we are at a position where we are trying to say that okay, range is 1 1, or the range is 2 2 or 3 3 or I anything like that. So as I told you that root leaf elements are represented by this kind of a thing, because leaf elements actually contain the values itself. So if that's the case, in that case, we can say that okay, the current element or the current node is a leaf node, and let's assign the value directly to it, right? So I'll assign the value that is in my array at that particular location, and I'll return. Else I'll have to calculate a mid. Now mid is you can actually write it as TL plus TR minus TL by 2. It's just more work, I think. So the general way of doing mid by like the general way I do it is TL plus TR by 2 simply. So I'll be doing that. With that I'll be getting a mid. Now I'll say that the left tree or the left child or the left subtree should contain the values from TL comma mid, right? And what's the value of the node? The value of the node is actually v into 2. as I explained that for any node, the left child has the value v into 2 and the right child has the value v into 2 plus 1, right? Okay, and the right child should contain the values from mid plus 1 to tr. I hope that makes sense. And then I'll have to update my tree. So when I'll getting back from this, right? So my left and right trees would have been populated. That's basic recursion. I hope that everyone understands that, right? Since my left and right trees are already populated, so I'll say that, okay, what's my sum? So my sum would be the sum of my left subtree and the sum of my right subtree, or the value that's there in my left child and my right child, right? So I'll do that. So this is how my tree is built. So this is all you need to build your tree. The tree building is clear.
Yes.
Anyone else has any doubt? Okay, cool. Let's move ahead. So once you have built you have done the tree building, you will come over here, right? Then let's say we want to get a sum. So for get sum, this is the function, right? Now get sum actually calls another function sum. Now I could have actually like not even used it, and I could have directly used the sum function. The only reason of using this function is because the sum function actually requires some hard coded values. So the sum function actually requires, let me see what the sum function is. Yeah. So firstly, it requires the value of the root, right? So the value of the root is always 1. So I had to pass that. Then it requires the left and right limit. Now the left and right limit over here are not the ones you are asking the range for, right? So they are actually 0 and n minus 1, because at the root itself, I want to tell that what is the size of the array that you are having. So the root actually has all the elements from 0 to n minus 1. So I have to populate it with 0 to n minus 1. And then I'll pass it the index or the range for which I want the sum, right? Okay, so from here I'll go to sum. Now what does sum do? Now sum does some basic stuff. If tr is less than tl, it means you are accessing some invalid range. It doesn't even exist, so return a 0. If my l is greater than tr, right? So what does that mean? So that would mean, let's say you are at a node. Okay, so your node has some value, let's say l comma r, right? Or let's call it tl and tr, because the nodes are actually for nodes I actually use tl and tr to denote that these are tree left and tree right, right? And the values you are looking for are maybe like lr, and you realize that your r is less than tl, right? So in that case, your this particular sequence would actually fall before this particular sequence, right? Now if this is the case, they have no intersection at all. So if your tl, right, if your tl is greater than r, in that case there's no intersection. Or the other case could have been that this was the case that your l is greater than tr. Now even in that case there's no intersection, right? So in that case you can simply return a 0. Or the other case is that your value that is okay, so the value of tl and tr are actually a component that is inside l and r. So by that, what do I mean? So let's say you were looking for the sum of range maybe like 1 to 8 or 1 to 5, and right now you are at a node that is having values 2 to 4. So now 2 to 4 is actually a subset of 1 to 5 itself, right? Because 2 to 4 is completely present inside 1 to 5. So in that way you can say that, okay, the entire node value or the entire value of this subtree is actually required or would be a part of the sum, right? So you can directly return it. Else you will calculate the mid element, that is tl plus tr by 2. Then you'll say that, okay, the sum that I want to get would be the sum that the left child would give me, and the sum that my right child would give me. So I'll simply return that. So yeah, that's it for the sum as well. Any problems in sum? Guys, any problems in sum? Okay, cool.
Nope.
Okay, cool. Let's move ahead. And the only operation that now remains is update, right? So update was actually pretty simple. Now update actually accepts two values, that is the index and the new value you're trying to update it to. So then it populates some hard-coded values that are 1, 0 and n minus 1. Now 1 is over, similarly like 1 is the value of the root, 0 is the left or the tree's left, and r is the tree's right. Then this is the update function. So similar checks are being performed over here as well, that I actually performed over here. So you'll see similar checks. So if tl is greater than tr, then return, or if the index is not present in the current range, then also return. Now you'll check if tl is equal to tr, that means you have come to a single you can say child element or a leaf node. Now it's obvious that you wouldn't have traversed the entire tree to get to a wrong leaf node. If you want, you can put an additional check over here that and IDS is equal to TL, but it's actually not required. It's obvious that you wouldn't have traversed the entire tree wrong to come to this leaf node, right? So if that's the case, then I'll update my tree element to the new element value. And for other nodes that are the for okay, so this is for the leaf node, and this is for the internal nodes. So for the internal nodes, I'll select a mid, right? And then I'll say that okay, update my left and update my right, because right now I'm not even concerned that okay if it's present in my left or if it's present in my right, because I know if it's not present in over that anyway, my children or the left child and the right child would take care of that. So I'll say okay, update these values, and now I'm gonna update my tree's value to whatever the sum of its left and the right child are. So yeah, that's it for segment trees. Are there any doubts? Any doubts so far?
Okay, one thing.
Yeah.
Just like you explained, it stores the actual values, some values in an array, right?
Right.
But it functions like a tree.
Right.
Yeah. Okay. That was the last thing I wanted to know.
No, so is there a doubt with that? Because trees, when you talk about trees, there are many possibilities in which you can represent them, right? So trees is kind of an idea that you want to have a node and then you want to have children's, but or the children.
Actually, no.
Mhm.
Uh, till now, I have seen trees made using classes and objects. I've
Right.
never seen them being stored in an array. So this is
Yeah. Right.
new to me.
Got it. Yeah. So actually, they can be stored and they can actually be represented. So anyway, you understood the entire concept, right?
Yes.
Okay, cool enough. So, also, like you are the target audience for this meet, considering that you are just in first year and you are not familiar with all these concepts. So, like talking in that sense, were you able to understand the entire concept over here, or were there points which you actually felt were tough to understand?
Um. Actually, that basic recursion part.
Uh huh.
I think I am a little weak in recursion, but like 2 3 days ago, I found out how I can recurse like without returning actually. So I understood that part, but maybe that would have been a little more difficult for other students. Maybe, not sure though.
Okay. Okay. Cool. So if anyone over here feels so, he can let me know. Or when I'll upload this video, if anyone feels that the way I'm teaching is going a bit over their heads and they're not able to understand the recursion part, so you can pause the video right over there, and you can ping me on Discord, or maybe I'll make another video where I'll explain this recursion thing in a bit more detail. Would that work? And anyone else has a doubt? Okay. Fine. So I'll move ahead now, bro. Thanks for the comment and for letting me know what can be improved. Okay, so this thing is done. Now let's move to questions now. Okay, so we are gonna discuss Codeforces question. Now one thing is pretty clear that if such a question comes in lead code, right, or in other placement exams or internship exams, then in most of the cases, they'll simply expect you to make a segment tree and that's it. So they'll not be expecting you to do some weird stuff with the segment tree or make it complicated. However, when a question from a segment tree comes in Codeforces or in other platforms which are related to CP, they don't directly ask you that okay, implement a segment tree and do this. So their questions are a bit tricky. So you have to understand that how you can use the segment tree so as to implement the algorithm you're aiming for. So with that, let me move to the questions. So these are the two questions I'm going to discuss. Actually, so I'm going to discuss this particular question, that is that is a problem D of div 2, and I'll give you this particular problem as a homework. Now the reason of giving you this problem as a homework is that this problem actually requires the understanding, or I can say the core understanding of it. So in order to solve this problem, you need to understand that how a tree actually looks and how we can manipulate it to get the values we are expecting. So I'll be giving you this part as a homework. However, if you face any difficulties, you can always let me know and I'll help you with that also. I think, okay, so might have messed it up, but anyway, let's see. Okay, yeah, so this part is definitely the homework thing, but I want to get that which part was there which I wanted to teach you right now. Let me just go over here and I'll check. Okay, so there was one question which I wanted to teach, and that was actually a good question. Yeah, anyways, week. So this is a E problem from Dev 2, and let's see what the problem states. So the problem looks pretty simple, but it's not that simple. Many people would think that we can easily do it using a set or a priority queue or something of that sort. So it's actually not doable with that, as far as I know. Okay, so the problem states that the Romans have attacked again, and this time they are much more than the Persians. But Chaper is ready to defeat them. He says a lion is never blah blah blah. Not interested. Okay, so Chaper has to find weakness in Roman army to defeat them. So he gives the army a weakness number. Uh, in Schaper's opinion, the weakness of an army is equal to the number of triplets I, J, K, where I is less than J is less than K, and the value of AI is greater than the value of AJ is greater than the value of AK, where AX is the power of the man standing at the X position. The Roman army has a special trait that the power of all the people in it are actually distinct. Now, this is something important that you need to understand. We'll explain that in a moment, that why it's important. Okay, help Shepard to find out the weakness of Romans, or how weak the Romans are, and then they are giving us the input. Now the input over here is that the first line contains a single number, that is n, that is less than equal to 10 to the power 6. That is the number of men in the Romanian army or the Roman army. Then the next line contains n different positive integers, that is AI, that would be the power of men in the Roman army. So we have to print a single number, that is the weakness of the Roman army. Cool. So for example, in this case, the values are 3 to 1. Now for the element at 2, there's an element to the left of it that's greater than it, and to the left of it there's an element that's less than it. So clearly for the element 2, there it's weak, because we are finding a pair that is 0 1 2. If we are doing zero based indexing, that is actually following this constraints that I is less than J is less than K, and A is greater than AJ is greater than AK. So any doubt in what the question is actually asking you for, or shall we move to the part where we can, analyze the algorithm for this? Okay, so I'm gonna open the iPad. Yeah. Okay, so the thing we want to find is that I is greater than J is greater than K, and AI, okay, sorry, I is less than J is less than K, and AI is greater than AJ is greater than AK. Or in other terms, I can say that for every element, for every element J, I want to find how many elements are to left of me and greater, and how many elements are to the right of me and greater. I hope that makes sense, right? So how
Wait,
would,
shouldn't it be smaller? Right of me and
yeah,
smaller.
smaller, right? Sorry, thanks, bro. Okay, smaller, right? Now how would we do this? Now one could say that we can easily start, and from left we'll put the elements in a set, right, or in a multi-set, but a set would signify would be sufficient because we are having different values. Cool. So from left to right we'll keep putting the values in a set, and then reaching at index I, we can easily use a lower bound operation, lower bound, to check what are elements are there in the that are actually smaller than me and are already covered. Now the problem is that lower bound already, though lower bound takes log n time, but then lower bound would just return you the iterator to a particular element. So it will say that okay, this is the like set you are having. Now, I'm not even concerned with how your set is made or what is made, but this is the iterator to the element that is just greater than you, right? Or I can use previous of lower bound, so it will return me the element that is less than you, just less than you. So it can return me that. But how do I calculate the number of elements that were actually less than me? So one thing is I can use a count operator over here, or a distance operator, which can tell me how many elements are there in the first between the first and this particular element. But this actually takes order of n time. So even if we are using this particular thing, then our time complexity becomes order of n square, which would actually fail. And a lot of people don't actually realize that distance formula or the distance function actually takes order of n time for containers which don't provide random access. So a lot of people might actually use it, and then post contest they'll realize that they are getting a TLE. So anyway, so what is a better way of doing it? So I can say that I'll take these elements, right, and what I'll do is that I'll provide them indices. So already they are indices, right? 0 1 2 3. What's the point of providing them indices? So the point is that I want to sort them, and then I want to provide them indices. So what would happen is that element that is the smallest, let's say this was 5, this was 6, this was 2 1, then 7, then 8, right? So this would have the index 0, this would have the index 1, this would have the index 2, 3, 4, and 5, right? So by this, what would happen is that when I'll reach at any particular index, right? Let's change the values a bit. Let's make it 4, right? Okay. So now when I'll reach at index 4, now I can check that how many indices were before me that were actually less than me. So less than 4, there were two indices, that is 2 and 3, right? Okay. I messed it up again. So this has to be 3, this has to be 4, this would be 2. Okay. So how many indices were before me that were actually less than me? So less than me, there were actually two indices, right? That were 0 and 1. Or I can check how many indices were there that were greater than me. So greater than me, there were two indices, that is 3 and 4, right? But even this is going to take us order of n time. So how can we use a segment tree over here to reduce the time complexity? So when I'll be going to my right, I'll maintain a tree, right? So a tree can easily be maintained. And since I'm providing over here, the indices are provided based on the values. So its actual index or the maximum value would go up to n, right? And I'll make a tree of 4 into n, or a segment tree of 4 into n. And then I'll say that whenever I visit a particular value, so when I visit 5, right, I'll see what's its index is, or what its sorted index is. So I'll see, okay, the sorted index is 3. So in my tree, go and update the location 3 as a value 1, right? Can I do that? Yes, obviously I can do that. Then when I'll go for here, I'll say that, okay, update the element at location 4 as a value 1. Cool. Then I'll come over here, then I'll say that, okay, go and update the location 1 as a value 1, so on and so forth. And now whenever I want to check that how many elements are there before me that have a value less than me, right? Now they over here they're asking greater than me, yeah, so I can do greater than me as well. So how many elements are there greater than me that are before me? So I can say that, okay, the elements that are greater than you and are before you. So before you is not even a constraint because I'm traversing from left to right. So at any index, I only know about the elements that were before me or were at the left to me. So I only need to check the elements that are greater than me. So how can I check that? So I'll know what is the, okay, let me clear this a bit. Okay. So I'll know standing at this particular element, how many, what's its index? So its index is 4, right? So what kind of elements do I want to check? I want to check the elements that have indexes greater than 4, right? Greater than 4. Okay, greater than 4. What is the last index that I can have? The last index is gonna be n minus 1, right? So I have to check the values in 5 comma n minus 1. That's it, what I'm gonna do. So I'm gonna directly check the values in 5 comma n minus 1. Not really. I'm actually gonna check how many like what is the sum of the values. Now why the sum? Because when I was updating it, for every element I was just setting this its value as 1 itself, right? So its value is being set as 1. Now that would mean that your location at 1 would have actually become 1, right? Location at 4, let's say 4 was this would have become 1. Then maybe this is 2, this is also 1, let's say, right? Then when you say that, okay, return me the elements which have a value which are in the range 5 comma n minus 1, or return me the sum of all the elements that are in the range in 5 comma n minus 1. So technically if you're taking the sum, then you'll gonna get the value of the count itself. Is this part clear?
Yes.
Guys, any doubts till this point? Okay, let me continue. So I see a few DMs over here, but I'll really appreciate if you could like put it right over here so that I can see if there's doubts pertinent to this session. Cool. Okay, so let me code it up now. I'll not be coding it. It would be a waste of time for you and me as well. So I'll just show you the code. Now the code is actually same that we have used. So this is the standard sum segment code that I showed you. So that same code is being used over here. There are no changes to that. And let me show you the other code. So over here I'm taking two arrays. One is the greater to left and smaller to right. Okay. Okay, after that I'm taking an empty array. Now why empty array? Because initially I wanted that all the elements in my segment tree should be set to value 0. So I'm taking an empty array. And then I'll be making two segment trees. Now why two segment trees? The simple reason for that is that once I'll be traversing from left to right to get to know that what are elements are there that are greater than me. Then I'll be traversing from right to left to know that what are the elements that are smaller than me. So I'm using two separate segment trees over here. You can actually use a single segment tree, then clear its value and then use it again. But yeah, this seems more intuitive and more easy to do. Then I'm gonna assign the locations or the values or the sorted values to it. So a easy way of doing it over here is that since we already know that all the elements are distinct, so we can easily take a set, right? After that, a set is already sorted, right? So I can start a loop, and for every element I can assign it id. Now since it's already sorted, it would get ids in sorted fashion. Now in this loop, what I'm doing is going from my left to right, and for every element I'm checking what is its sorted location, right? So its sorted location would be available in that particular map which we had populated over here. So I'll get its sorted location. Now I want to check elements that are greater than it, right? So, and greater than it and to its left. So those elements would actually be given by log plus one. So log plus one is actually the value you are having, right? So you want to check greater than that, right? So you'll be having a check at log plus one, and you want to go to n minus one. Now id would actually be equal to n because it's incremented in time. So you could write n minus one or log minus one, whatever, id minus one, whatever you want to write, and then you're gonna update its value to one, right? Then you're gonna say do the same for smaller to right. So then you're gonna say that okay, I'm having a value log. I want to check what are elements are there that are smaller than me. So the elements that would be smaller than you would be present in the tree 0 to log minus 1, or in the subtree 0 to log minus 1. So you'll get that value, you'll store that value in small to right, and you'll also update that current value. After that, what would be the final answer? So for every index j, you want to multiply the number of possibilities you were having for smaller elements to your left and the number of possibilities that you were having for the greater elements to your greater to your left and smaller to your right, sorry. Yeah, so you will be doing that, and as a result of that you will be having the answer over here. Yeah, so that's it for the solution. I hope that actually made sense to you guys. Let me know if you feel otherwise, if there are still any doubts. And I'll put this particular problem. This is actually an interesting problem, right? I'll put this in the Discord channel as well.
Can you explain the multiplication part once
Yeah,
again?
sure. Okay, cool. This one, right? Rest is clear to you?
Yes.
Okay, give me a second. Okay, so let's say this is the element, or let's say this is the element 2, right? Over here you had the 1, and over here you had the 3. Let's say this is the array. It was smaller to your right or what? Give me a second. Okay, so it was greater. Okay, so this is 3 to 1, right? Now at 2, how many elements do you have to your left that are greater than you? You have one element, right? How many elements do you have to your right that are greater than 1? Or that are greater than you? That is one element also. Now let's say there was some other element. Let's say there was element 0. I don't know if 0 is a possible value over here, but let's just assume it for now. Now let's say there was one more element that was actually 0. So the count over here would increase to 2.
Yes.
That's fine. Okay. Now, technically, when you want to know that how many pairs exist, so one pair would be 3, 2, 1. One pair would be 3, 2, 0. That would be the two values possible,
Yes.
right?
I think there would be one more like 210.
Yeah, so 210 would be there, but over in 210, right, the j would be 1, right? So that
Yes.
would automatically get calculated when we'll move our cursor to the next
Oh,
value.
oh, yeah. For j equal to 2, there will be 2 only.
Yes, for j equal to 2, there would be two values.
Yeah.
Now, since you can multiply or since you can choose, so the way of doing it mathematically is, so this is the left set, this is the right set. From the left set, you can choose any one element, right? From the right set,
Hmm.
you can choose any one element. This always has to be chosen. So, in how many ways can you do that? So, the ways for choosing one element from here would be actually NC1, or it's simply N. NC1 is simply N, right? Or
Yeah.
let's say LC1, so it's L, and let's call it RC1, so this is R, right? Then you multiply L and R.
Oh, the number of combinations. Okay, I got it now.
Yep. Cool enough.
Yeah.
Anyone else has a doubt?
Sir, can you please explain that part once again? Get some function कैसे दे रहा है count?
Okay, bye. Get some function now. Give me a second. Uh, okay, for this particular problem, you mean?
Yes, yes, sir.
Okay, okay, okay. Cool, got it. Okay, देख भाई, तेरे पास अभी वैल्यू है 2, मतलब तेरे पास कोई भी वैल्यू है, मान लो तेरे पास 5 है अभी वैल्यू करंटली एरे में आई हुई, ठीक है। तो टेक्निकली तेरे को चेक कौन सी वैल्यूज़ करनी है, 0 to 5, राइट। तो
सर।
मैंने ऑलरेडी इनको इंडेक्सेस प्रोवाइड कर रखे हैं। तो लेट्स से इससे पहले तेरे पास जब भी कोई वैल्यू आई होगी ना, जैसे तेरे पास कोई वैल्यू आई 6 7, देन यू हैड 1 2 बिफोर इट, राइट। सो टेक्निकली इनके इंडेक्सेस ऐसे होंगे कि जो 1 और 2 के इंडेक्सेस है ना, वो लेस देन 5 का इंडेक्स होगा। तो लेट्स से इस वैल्यू इंडेक्स वाज 1, दिस वाज 2, दिस वाज 3, दिस वाज 4, दिस वाज 5, ठीक है। ऐसे इंडेक्सेस ऑलरेडी प्रोवाइड कर दिए मैंने सेट में लेके और सॉर्ट करके एक बार। इतना पता है,
यस सर।
इतना क्लियर है वैसे।
यस सर।
ओके कूल। सो जब मैं 5 पे आया, सो आई सेड कि ओके इसकी इंडेक्स वैल्यू तो 3 है। तो आई वांट टू गो इन माय ट्री एंड चेक फॉर द सम ऑफ एलिमेंट्स इन द रेंज। अगर मेरे को ग्रेटर चेक करने हैं तो आई विल से दैट इज ग्रेटर देन 6 और ग्रेटर देन 4 एंड बियॉन्ड, राइट। सो लेट्स से मेरे टोटल नंबर ऑफ इंडेसेस 8 बन रहे थे। सो आई विल से ओके गेट मी द इंडेसेस इन द रेंज 4 to 8, और गेट मी द सम ऑफ
ओके।
इंडेसेस और गेट मी द सम ऑफ एलिमेंट्स इन द रेंज 4 to 8। अब होगा क्या, इधर मैंने ट्री में एक्चुअली 6 7 स्टोर नहीं करवाए थे। तो जब मेरे को 6 मिला था ना, तो मैंने बोला था इंडेक्स 1 पे जाके ना और इंडेक्स 4 पे जाके इसकी वैल्यू 1 सेट कर दो। जब मेरे को 7 मिला था तो मैंने
ओके।
बोला था
ओके।
इंडेक्स 5 पे जाके इसकी वैल्यू 1 सेट कर दो।
ओके 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 सर, अब क्लियर हो गया।
क्लियर हो गया, कूल।
हाँ सर।
गाइस एनीवन एल्स? Cool guys, if anyone still has a doubt, let me know, or I'm gonna close the meet. In general, was this helpful? Were you able to understand the stuff, or are there any recommendations that you could give?
Introduction to segment trees was really helpful.
Okay bro, thanks a lot man. Yeah, I actually plan
हाँ,
on
थैंक यू सर।
cool man, welcome. Yeah, so I actually plan on giving you a brief idea about lazy segment tree as well. So I actually want that you become comfortable with segment trees before we move to lazy segment trees. Also, one important thing is that you don't need to study binary index trees and stuff, because a segment tree is more powerful than the binary index tree. So whatever operations or whatever algorithms you can solve using a binary index trees, you will always be able to do that with a segment tree, right? And also a lazy segment tree is always powerful than a segment tree. So in that way, what I want to do is that I want to teach you lazy segment tree next. But before that, I want you to solve some problems. Now I'll share this, but I've already shared this one problem. I'll actually share the entire link with you. So this is the link, and this actually has a lot of problems, right? It's possible that you kind of feel lost and it feels a lot tough, right? But that's actually okay. Why it's getting copied as a image, I have no clue. Does anyone know why it's getting copied as an image?
Um, no idea.
Okay, no
I
worries.
think
Yeah.
because of the font color and the software you're using.
uh, that's pretty
Copy and paste it in some
no
text
worries.
file,
I'll
probably
click it
notepad.
from here itself. No worries about that. No, like workarounds are always available. It's good to know.
Yeah.
Command Shift V to remove font styles. Oh, Jugal bhai will definitely remember this thing. Okay, thanks. So yeah, the thing I was saying is that you don't need to like study binary index trees and stuff. Lazy segment trees is one thing I want to teach, but I want you to get familiar with this particular topic before I teach lazy segment trees. So for this particular week, I'll expect you guys to go through this particular blog and do all of these things, right? Or perform like solve these questions. Now this blogs actually has questions that are based. So these are classic segment trees. For this we have already studied today. I would advise you to go for the other questions, and it's really possible that you go to a question and you're not able to solve it. This particular question don't solve it actually. It's solve this. I don't know why he has mentioned this question. It doesn't requires segment trees per se. This is solvable easily by a set. So don't solve this question, I'll say. But yeah, you can try for the other questions. Definitely do this question. This would actually check your concept clarity, right? If you feel yourself stuck on a particular question, then you can ask on the group itself. I myself would try to help you out. If I'm not available, then probably someone else would. Okay, मेरे को react करना था यार. Yeah. Okay, guys. So thanks a lot for being in this video. I hope you found this helpful. Cool, guys. Bye bye.
थैंक यू सर।
Thank you,
No
sir.
worries. Okay.
Bye bye.
Bye bye.